So number 6. So in problem 1, we're asked to evaluate the limits without L'Hopital. So we're going to do the first one, which is limits as x goes to 0 over x. And this might be a little bit tricky because you're tempted to say that you have a 0 over 0 case, 0 over 0 case. But the difference is that this is actually 0, like in the sense that it's 0.0000. No ones, it's just 0. Oh, yeah, perfect. All right. The idea is that in this case, the limits up top, you don't have something that goes to 0. You just have pure 0, like 0.0000. This thing, this x, is going to be something really small. You can imagine it being something at 0.001 or something at some point. So difference is x goes to 0, but this is pure 0. Okay? It doesn't go anywhere. It's just 0. So the idea is that this is just, you can consider it as 0 over any number. This just gives you 0. Okay? So again, the argument was that the 0 up top is pure 0. It's not something that goes to 0. It's not something very, very, very small, how you would characterize this x. It's just 0. Okay? So again, this is another way of writing it is this is pure 0. X, although the limit of x is 0, x goes to 0 is 0, this is something very small. This 0 up top is not something very small. It's just pure 0. Okay, any question on this? Cool. On problem number B, I have exactly no clue how you're supposed to solve this without just claiming the exponential is bigger than x. Of course, without using L'Hopital. Next 5. Okay, so this is it. And the way I would solve this, I would just say this is equal to infinity because exponential bigger power function. And again, this thing is something you can use in the exam. So if you haven't memorized it by now, I would highly recommend memorizing it or keeping it in mind because it just makes some things really easy. Intuitively, why is this? Because just, I don't know, if you graph something, a power function or E of x or something, at some point, E of x literally just becomes vertical function increasing. At some point, E of x just looks something like, I'm sure I guess it just goes something like this and it becomes vertical at some point. It just grows absurdly fast. You can give me any x you want. It's not going to, you can give me x to any power you want. It's not going to go as fast as this. That is kind of the argument intuitively. And further down, further down the road, we're going to prove it formally. But right now I can't use L'Hopital, so I can't actually prove it. But again, exponential, bigger power function. Really important. One key to this is when x goes to infinity, this is true. When x goes to 0, limit when x goes to 0 E of x over x. Well, in this case, it's still going to be infinity because this is 0, so this is 1, and this is 0, so it's 1 over 0. This is just infinity. But this argument, exponential bigger power function, only holds when x goes to infinity. So I'll actually write only holds when x to infinity. Okay, when x goes to 0, you can't really use that. You can't really use that power function dominates everything when x goes to 0. Okay. Good. Now we're on to using the L'Hopital rule. Problem number 2. Problem number 2, you have case A where you have limit when x goes to 0 of log of x square root of x. Okay. And yeah, I'll remember that one. Okay. Before applying L'Hopital, always check for the case. So in this, although the problem tells you to apply L'Hopital, you gotta be like, I know it's hard to say, but you gotta be like, problem, you're wrong. I gotta check people applying it, kind of thing. So I'm gonna check it. If it works out, I'm gonna apply L'Hopital. If it doesn't work out, it is what it is. So I'm checking the cases. When x goes to 0, this is 0. Square root of 0, this is 0. When this is 0, this is log of 0. What is log of 0? I said, I think yesterday in class, this is minus infinity. So I have minus infinity over 0. This is not a L'Hopital case. I cannot apply L'Hopital. It is wrong to apply it. Now, minus infinity over 0, something very, very big, something very, very small. I think I wrote this as well at some point. This is just minus infinity. Yes? Okay, so think of it like this. If log of A is equal to B, then e to the power of, then A is equal to e to the power of B. Okay? Now, A is 0, okay? Log of 0. Let's say it's some B thing. I don't know what it is. Then it means that 0 has to be equal to e to the power of B. Now, remember I told you repeatedly that log of 0 does not exist. It does not exist as a number. The reason being this, any power of e reason, to any power is never going to give you 0. Any number you put here is not going to give you 0. That's why log of 0 is not defined. And that's why in all the problems you always check for log of 0, not for log not being 0. The reason being in this case is that if I take a really big negative number here, e to the minus 1,000,000, 1,000, okay, it's just 1 over e 1,000. And this just, as you can tell, is a really, really small number. So I'm getting close to 0. And that's why I'm saying that the solution to this would be minus infinity. Some really, really, really big number, negative. That's why log of 0 is minus infinity, or goes to minus infinity. Again, log of 0 is not defined. Let's be clear on this. Log of 0 is not defined. In a limit setting, you can say that log of 0 goes to minus infinity. Okay? Cool. So in this case, you can't apply L'Hopital. One way which we can change it and actually apply L'Hopital is this way. Let's do limit when x goes to 0 of ln of 1 plus x square root of x. Okay, let's do this one. Let's evaluate it this time. x0, this is 1. Log of 1 is 0. x0, this is 0. So this is a 0 over 0 case. Okay, so now I can apply L'Hopital after changing it a little bit. Does everyone understand my evaluation? I said when x goes to 0, this x goes to 0 from the ln. 1 plus 0 is 1. ln of 1 is 0. And then square root of x, we already knew it goes to 0. So I have 0 over 0 case. So now I can apply L'Hopital, which is just limit when x goes to 0. Take a derivative of this thing. This is 1 over 1 plus x. Derivative of this thing is 1 over 2. 1 square root of x. Hope I'm right. I'm not going to mess it up, but that looks about all right. Okay. And now let's see what we get again. This is just equal to limit x goes to 0 of just flip everything here. I put this up top and this down below. And I get 2 square root of x, 1 plus x. Okay. Now we evaluate this function again. And I get, when x goes to 0, this goes to 0. 2 times 0 is 0. 0 here, 1. So I have 0 over 1. That's just 0. Okay? So I think I received this question. You can never know looking at it, without evaluating whether you can apply L'Hopital or not. My example is simple. By just adding a 1, I'm sure, it's the difference between allowing you to apply L'Hopital and not allowing you to apply L'Hopital. This 1 here. Yeah. No. This is a completely different problem. Like, they're completely two different problems. I just more or less corrected it or gave you this example. Of course, you're not allowed to add 1. Do not do that, please. No. This would be like, problem number I and problem number I second or something like that. They're completely different problems. Okay, just to be clear on it. I just gave this as an example where you can actually apply L'Hopital. So this is another example. It's not the same thing. Example. I'll even caps lock it here. Not same problem. Right? Okay, not same problem. I'm just correcting it so we can apply L'Hopital to it. Okay, now, any other questions here? Just, I think I broke it. Okay, we fixed it. No other questions here. Okay, let's move on to the next one. Next one is limit when x goes to 1 of x minus 1 ln of x. Okay, now, first thing is to evaluate it. We evaluate it and we see that if this is 1, this is 0, log of 1 is 0, so this is just 0 times 0, which is just 0. Okay. Again, always we need to evaluate before L'Hopital. I don't think this was the intention of the problem necessarily, because it says apply L'Hopital. There's nothing to apply to it right now. It's just 0. But I can change it for you if you give me a second. Okay. This is a stretch, but sure, let's do this. Let's do, okay, correction problem or whatever. And we're going to try to keep it simple form. ln of x. Okay? The difference is that if we try to do the same exact trick we did before, okay, just evaluate and hopefully it works out. I'm going to get, this is 1, this is 0, 1 over 0, this is infinity. This is 1, log of 1 is 0. And I told you that infinity times 0 is undefined. You don't know what it is. So question mark, I can't answer that. Infinity times 0, not defined. So now, the standard strategy is to create your fraction and apply L'Hopital. Okay? Now, I've already given you the fraction. So your fraction is just limit x goes to 1 of ln of x minus 1. And again, this is 1, this is 0, this is log of 1, this is 0. So 0 over 0 case, I can apply L'Hopital to it. Okay? And if I apply L'Hopital to it, I get limit when x goes to 1 over x over 1. So limit when x goes to 1 of 1 over x is just 1. This would just be like a correction, a small correction problem. But it's always important to evaluate your limits, because sometimes you can apply it, sometimes you cannot. And you can't without, without taking a pen and paper and seeing what the values actually are, you can't tell just by looking at it magically, oh, I can apply the calculator, or no, I can't. Okay? Any questions here? Cool. Now, problem number 3, the one with continuous. Yet I don't think necessarily that you're actually going to have to prove on the exam any continuity. I don't know. I think it's more of a trick for limit exercise, but I think it ended up being a little bit more confusing than it should have been. So integral, not integral, sorry. That's x0. Okay, so this is your function. You're asked to show continuity around 0. Before we go into that, I would just give like 1 second to basically make sure that you understand how these functions look like, how this function looks like. So the way you do it is, for example, you look at f of 1. Okay, if I look at f of 1, 1 is greater than 0, so I look here. Okay, I look on this branch of the function. So f of 1 is 1 times log of 1, which is just 1 times 0, that's 0. Okay, now if you look at f of minus 1, minus 1 is smaller than 0, so I look here. This is minus 1 squared, is just 1. All right, just so you make sure how the function is defined. I'm going to try to hand graph it. Again, I don't really use Wolfram Alpha or whatever you guys use. So if it doesn't look like how it should, just take it as with education purposes, okay? So I think it looks something. This is just me graphing it freestyle kind of. So again, your f of x is here, my x is here. If it's smaller than 0, it's x squared. So I'm thinking it's going something like this. And then it goes, so this part of the function is going to be x squared. And this part of the function is going to be something like that. This is x, ln x. Okay, does everyone understand how it works? How this function is defined? On this right-hand side quadrant, it's x ln x because of this definition. And on the other side, it's x squared. I hope this example with f of 1 and f of minus 1 makes perfect sense to you guys. Okay, now, what does it mean to be continuous? I'll give you the general definition. The general definition is that when you take limit from x to a plus, which I think you use that notation, this notation means that you're coming from the right-hand side. So x greater than a of f of x has to be equal to f of a. If this happens, it is said it's continuous from right. Okay, the graph that I would use is this one. Again, it's not supposed to have anything to do with the problem because I'm giving you definitions right now. So let's suppose we have something like this. A point here. And I'll go something like that. Okay. The idea is that this is my a f of a. And now I basically take the limit as I go from here. So I take limits from right and then limits from left. Does that make sense? So I have this point, and I'm basically just taking the limit of the function from the right-hand side and the limit of the function from the left-hand side. Right, and I'm checking if those limits are equal to the value of the function. That is all. So again, let's interpret what I said here. Limit of f of x, so this function, for as x goes to a, so I'm going to a here, with x greater than a. So I'm coming from the right-hand side. Okay, these values are greater. If this limit here, this point that my limit point is equal to f of a, it is continuous from the right-hand side. Now, obviously, the opposite is if x goes to a minus, x smaller than a of f of x is equal to f of a. So I'm coming on this side, then it's continuous left. Okay, and if it's continuous left plus right, then it's just continuous. You don't say anymore, you just say it's continuous at that point, at point A. Okay, does everyone kind of understand the definition? I just got to check for those limits and see if they're equal to the value of the function. So now we're just going to take the definition exactly from here and see if we can prove our function f, this particular f. So I'm asked to look at f of 0, look at 0. The first step I would say is just see what f of 0 is. And then here I'm going to use the definition of the function. Let's see. Okay. For f of 0, 0 goes here. So I just get 0 squared is equal to 0. Okay. Now let's see. Limit from the right-hand side, let's say, to 0 with a plus, x greater than 0 of f of x is equal to what? Okay. What is f of x in this case? That is the question. That is how you should think of it. And you look at your function up top. So I'm going to copy the limit. Limit x goes to 0 with a plus, x greater than 0. If x is greater than 0, then it means I am here. Okay? So it means I have to compute x ln of x as x goes to 0. Fair? Now, I have to evaluate this limit. If this limit is equal to f of 0, 0, it is continuous from the right-hand side. If it's not, it's just not continuous. Cool. Now, let's evaluate this. So again, the step was, I took the definition of continuous from the right-hand side. I just plugged in my function because x goes to 0, x greater than 0. Again, this is the condition. This condition forces me to use this side of the definition. Okay, I'm using the definition of the function for x greater than 0. So I'm using this formula, I plug it in here, and now I'm going to try to evaluate this. That's my thought process. Okay, now what is this equal to? Well, we got to look at it for a second. And this x goes to 0. This x goes to 0. The problem is log of 0 goes to minus infinity. Okay, so I have 0 times infinity. That is not defined. So I need some trick. I need to get to the L'Hopital so I can apply it and actually solve this problem. So the way I'm thinking is this is just equal to limit x goes to 0 plus x greater than 0. This x, I can just write, and here's the trick. I think I told you in one of the previous summers or something, that this, when you have 0 times infinity, you create your fraction by using 1 over 1x. Okay, so I'm going to do the exact same thing. No new strategy. I'm just going to replace x with 1 over 1x. Again, the reason being that x is just x is equal to 1 over 1x. That is the trick that I'm going to use here. So I'm going to get, I'll just write it here. I'm going to get limit when x goes to 0 with a plus, x greater than 0, ln of x over 1x. Okay? So I apply that trick. Again, what guided me to use that trick is the fact that I only know L'Hopital for undefined cases. So I have to create a fraction. L'Hopital only applies to fraction. I need to create a fraction. I created my fraction. Let's evaluate it now. X goes to 0. 1 over x goes to infinity. X goes to 0. Log of 0 minus infinity. So this is minus infinity over infinity. We're good. This is a L'Hopital. Okay, I can apply it. L'Hopital. So limit, copy everything again. And I get 1 over x minus 1 x squared. Multiply everything around, or however you want to call it. And I get, simplify, I don't know, whatever works. And I get limit x goes to 0 with a plus, x0 of x, of minus x. That's just, when x goes to 0, this goes to 0, so it's just minus 0, so 0. Okay? So remember, 0, but remember 0 is actually f of 0. So this is actually equal to f of 0. Fair? So let's take stock of what happened. I computed this limit, the limit to the right, and as x goes to 0, and I got that it's equal to f of 0. What does this mean? Continuous right. Check. Any questions on this? Because this is literally what I'm going to do for everything else. Like everything else is just the same. At least the procedure is going to be exactly the same. So any questions on this? All right, then let's just do the limit as x goes to 0 with a minus, so x smaller than 0 of f of x. Now, this is much simpler. Why? Because if x is smaller than 0, I have to use the other like channel, or however you want to call it. So this one. X is smaller than 0, so I got to use x squared. And now I'm going to get limit x goes to 0 with a minus, x smaller than 0 of x squared. When x goes to 0, x squared just goes to 0 as well. So this is just 0, f of 0, continuous left, check. So done, I don't know, function, I don't know, f continuous at 0. So problem is done. Okay? It all stems from the definition. I just took the definition, replaced with my values, and I had to compute this limit here, I guess. This was something extra. Okay, no questions here? Cool, let's just move to part B, I think, which gave me something else. Sorry about that. Okay, so part B goes around the lines of B, f of x. It's the same definition for x greater than 0. And I just have a 2 here. Oh, I just copied. Okay, this is the new definition. As you can see, it's quite similar to the previous one. Just I have a 2 difference here. Now, intuitively, what I'm saying that my graph is going to look like is something like this. I think my graph is going to look something like, so this still stays the same. It's supposed to be xfx. But the problem is that x squared plus 2 start from here. Okay? And this is what it's called like a, so this would be x squared plus 2. This would be x ln of x. So, as you can see, this is a classic, this picture of continuity. What do I mean? What do you mean by this? The function just goes until here, and then it just jumps here. Okay, it just jumps. When you have jumps like this, it's usually not continuous at those points. Okay, that's kind of the graphical illustration of discontinuity. So if I have this graph in mind, or I could graph it in my head, I shouldn't be surprised if I don't get continuous, okay? Because this is how it's gonna look kind of like. Anyway, let's see what we get, and you know, this maybe I'm wrong. Maybe this is just my intuition going wrong. So again, we do the exact same procedure. I compute limit as x goes to 0 with a plus, x greater than 0 of f of x. Same logic. I will have so okay, since x is greater than 0, I will use this rule over here, and I get again limit x goes to 0 with a plus, x greater than 0, x ln of x. Now I know this is 0. Okay, I'm not going to compute it again. I hope everyone is convinced that it's 0. Now, is this equal question mark to f of 0? Well, I don't know. Let's see what f of 0 is in this case. What is f of 0 in this case? F of 0 is equal to 0 smaller equal to 0. So this is where I'm going. It's equal to 0 squared plus 2. This is just 2. Okay. So I would need to get 0 equal to 2, which is false. So at this point, I can say not continuous right side. Okay. And now we have only one side left to go. That's the time. Fine. Okay, we're going to do only one case left, and that is f of limit when x goes to 0 with a minus, x smaller than 0, f of x. In this case, when x is smaller than 0, I have to use the other rule, this one. And this is just limit x goes to 0 with a minus, x minus 0, x squared plus 2. And I've been asked this question so many times. When you see constants just purely standing in the limits, they can be taken out. They just don't disappear. They can be taken out. So this is the same as writing 2 plus limit of x squared, x 0 with a minus. Okay? The constants do not disappear in this case. They just pull out in front. Now I know that this is 0. So this is 2 plus 0. That's 2, which is equal to f of 0. So it is continuous from left. And that's, I'm done. It's not, it's continuous from left, not continuous from right. It's all that the problem asks it to do. So any questions on this? This step right here, again, it's one of those simple steps that just simplifies a lot of things and helps you not mess up. So yeah, keep that in mind. Okay. Okay. Now we're gonna move to a polynomial, which I found that it wasn't even defined for you guys. So let's see how we can work around that. So you're given in problem number 4. We're just gonna do part A, and then after the break, we're gonna do B and so on. So problem 4. You have P of X, a polynomial. A standard polynomial looks like, it looks like this. I'm gonna write the formula now, and then I'm gonna explain. Okay. This is, oh, you can't see it. Yeah, I should have said something. Okay, so this is how a standard polynomial looks like. If you don't like this writing, just think of it as any sum of powers of x. Any sum of powers of x you can think of, that is a polynomial by definition. Okay? This is the formal way of writing it. But I guess the way you can think of it is any sum of powers of x. With any coefficients, any signs, doesn't matter. that is a polynomial. So for example, you know, x247 minus 37x squared plus x24 minus 3, that is a polynomial. Any powers of x, any combination of them forms a polynomial. Okay? And now you're asked to consider the limit. Limit EAX minus PX, x goes to infinity. And then the first question is this infinity minus infinity? That is your first question. And I would not expect you guys, since you just learned basically what a polynomial is, I would not expect you guys to evaluate this part, the second part, and tell me if it's infinity or not. But I would have expected to evaluate this first part, e to the power of ax. So e to the power of ax goes to infinity if and only if a is positive. Okay? If a is not positive, then EAX will go to 0. Why is that? If a is negative, and you know, if a is 0, this just is equal to 1. If a is 0. But so I think the first case is pretty. If a is positive, that's pretty obvious. But the question is, why is the second one true? The reason being, if this is negative, I can just write it as 1 over e minus ax. This is positive this time, okay? So I have 1 over infinity kind of thing. So this is 0. This is positive. So this goes to infinity, and this is 0. Okay, so this question is, these are like 3 cases, depends on the value of a. If a is positive, then you have infinity, otherwise 0, and otherwise 1. Now what about a polynomial? Again, so this up top hopefully made sense, or at least you can try to understand it. This polynomial rule, there's not, since the sum of powers of x, the polynomials either go to infinity or they go to minus infinity, depending on the dominant coefficient, which is the coefficient of the biggest power. The coefficient of the biggest power. Okay, infinity minus infinity, depending on the coefficient of the biggest power. So what do I mean by this? For example, when x goes to infinity of x goes to infinity, this is a polynomial, right? I said any powers. And at the same time, limit when x goes to infinity of minus x is minus infinity. This is a polynomial as well, right? They're just powers. I said any powers, any signs. So that's why, and this is obviously the simplest case. It just goes for any number you can create, any power you can create. Yeah, so now that we've done the case A, we're gonna move to part B after the break, I guess. Tune in after the break kind of thing. So yeah, let's take a 10-minute break and we'll get back to solving it. So let's do point B. So, this is not point B. Okay, point B is this one, which asks us to find the limit of x infinity e to the ax minus p of x. And now, if you wanted to be thorough in solving this, the way you should do it is more or less take all the cases that we've done here and basically, analyze each of them. For example, case one where A is negative and P of X is infinity, right? In this case, I would get limits of AX minus PX, X goes to infinity. This is going to go to 0 as we talked, and this is infinity. So this is minus infinity. Case 2, A smaller than 0, P of X plus minus infinity, and so on. This would be like the completely formal way to do it. You just take all the possible cases in combination and see where the limit goes. Now, most of these cases are completely not interesting. As you see, we have 0 minus infinity. We're not really interested in that. It's quite simple, right? So we're going to jump all the way to the important case, which is this infinity minus infinity. I think what the problem or what the professor wanted to say more or less is solve this limit in a case of infinity minus infinity, because that's the only like interesting case. All the others are just 0 minus infinity or 1 minus infinity or something like that. So they're not really interested. So we're going to solve it in this case, which in particular is A greater than 0 and P of X is infinity. So we're going to have the limit of EAX, PX. This will go to infinity. This goes to infinity. And why I said this case is interesting, because usually undetermined cases are interesting problems. What did we learn about infinity minus infinity? We don't know where it goes. It's undetermined. This limit, this general thing, infinity minus infinity, I can give you examples where this limit goes literally to any number you want. You give me a number, I create a limit for you. Created a limit of this type that goes to that number for you. So this does not go to infinity or 0 or whatever you can think of. It can go to all of them. So what do we do here? He gives the hint, but I also gave this as tricks how to evaluate. This is a case of undetermined. Okay, you don't know where it goes. The only trick you have for undetermined things is L'Hopital. Everything, you don't know anything else. You just know L'Hopital. So the trick here is, again, create a fraction. How do we create a fraction? We either use the hint or we just factor something out. So X goes to infinity, EAX, 1 minus PX, EAX. Okay, I just created my own fraction. I just factor it out. So I have this fraction. Now, this goes to infinity. This is 1. This is infinity over infinity. So I can attempt to compute this. Now, I could give you the general case and try to solve it and be done with it, but I don't think it's going to build the intuition that you need for this type of problem. So my suggestion, and a lot of the students didn't quite see until they solved it, which was a struggle, why I'm saying just take an x squared plus ax plus b. Just take this as an example. And after you're going to solve this, it's going to make sense why it works for the general case, for this ugly, ugly thing. So if we put this in, I'm only going to evaluate limit of x goes to infinity only of this fraction. This is the only thing I'm interested in. So I'm going to evaluate x squared plus ax plus b over EAX. And now, you have infinity up top, infinity down below. So infinity over infinity, L'Hopital, limit, x goes to infinity. What do I have left up top? 2x plus a over EAX. Oh, sorry about that. A in front. Oh, okay. I didn't realize this A is the same as this one. Sorry for that. It doesn't matter though. But let's put a C here so it's clear, I guess. These are just constants, right? They're just numbers. Okay, cool. Let's evaluate this one again. When x goes to infinity, this goes to infinity. So this goes to infinity, and this obviously goes to infinity again. So this is an infinity over infinity case. Apply L'Hopital again. And I get limit x goes to infinity, 2 over a squared EAX. And when you evaluate this, you get constant, so 2. And this is infinity. So you get 2 over infinity, which is just 0. Okay? Does everyone follow the L'Hopital here? I think it's pretty standard, pretty simple, this L'Hopital. Okay. Now, I have proved that this limit goes to 0 for this particular case. Now, why does it work in the general case? Well, let's take stock of what happens to the power, okay? So let me use maybe a different color to emphasize. Here. Right, let's use red. Okay. So what's the idea here? I started with this x squared here. Yeah. I started with this x squared here. Okay, that was the biggest power I had in the upper part. Okay. I applied L'Hopital to it once. What happened to it? I got x. I applied L'Hopital to it again. I got x to the power of 0 here. Basically just disappeared. Basically just went away. At the same time, look what happened to the denominator, the lower part. EAX, EAX, EAX. It's unchanged. So that is the idea, that whatever polynomial you put on top, if you have e to the ax underneath, I can just apply L'Hopital over and over and over and over again until up top I have nothing left. I'm just going to have a constant up top, but e to the ax is never going to go away down below. Okay, so again, the argument I use is the following. If I take this huge polynomial, the general case, and I want to compute the limit of x goes to infinity of Pn of an xn plus an minus 1 xn minus 1 plus dot 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 plus a1x plus a0 over eax. The idea is that if I apply L'Hopital to this n times, for example, everything up top is going to disappear. That is the idea. That if I apply L'Hopital to it, this is let's write it. Infinity over infinity, L'Hopital. I don't mean to write it. Okay? We're going to get limit x to infinity. The dominant power is just going to be an times n times some xn minus 1. Okay? It's a plus something, I don't know what it is, over aex. Okay, again, the trick is that this exponential doesn't go away ever. It just stays untouched there. While the biggest power, the strongest thing, just dropped. Okay? If I apply it again, I hope everyone got the trick by now. If I apply L'Hopital again, I'm going to get limit of n minus 1 xn minus 2 plus something, I don't know. Okay, and again, logic is ax untouched. This xn minus 2 keeps on dropping. So eventually, I'm just going to, if I just apply it a number of times, I'm going to get limit x to infinity of some number here. I don't know, some constant here, over a to some power, I think that's n, eax. So constant, infinity, 0. Does it make sense? So this is the formal proof why the exponential dominates any power or any x to any power you can think of. This is the reason that if you were to prove it and apply L'Hopital to it, the power would just drop slowly one by one. The exponential would just stay untouched. That's the logic behind it. Okay, so now to answer my my initial problem, which was this one. What is limit when x goes to infinity of eax 1 minus px over eax? And this is 0, so I have infinity times 1 minus 0, infinity times 1. This is just infinity. Right? So that's the thing. Exponential is much, much stronger than any polynomial or any power function or anything like that. That is the formal proof to this. Any questions on this? Okay. Cool. Problem 117 in the compendium. Okay. Sorry for the scrolling. And we get this one. Problem 117 says, compute the limit when x goes to 1 of ln x minus x plus 1 of x minus 1, 2. This is your limit. We take 1 second to evaluate it. If x is equal to 1, this is 1. So this is ln of 1, which is equal to 0. This is 1, oh, this is 1, 1, 1 here. So I get 0 over 0. That's my case. So I can apply L'Hopital to it. And I'm going to get limit, if x goes to 1, of, what do I have left? 1 over x minus 1. And down below I have 2x minus 1. Okay, I just took a derivative of applied L'Hopital. Took a derivative of the top, took a derivative of the bottom. And this is what I got. Now, I guess let's evaluate this one as well. I have no other ideas. If you have any other ideas, just let me know. I just don't care, I guess, enough at this point, so I can evaluate it. Yeah, so let's see. What do we have here? This goes to 1. 1 over 1 goes to 1. So this goes to 0. This is 1. This is 0. So I have, again, 0 over 0, L'Hopital. And again, you can maybe do something. You can maybe get the limit from here. I haven't really thought of it, but I'm just, I'm being corrupted. I'm just starting to take the easy way out, I guess. So what's this derivative? It's just minus 1 x squared. And this derivative is just 2. So I got limit as x goes to 1 of 1/2 minus 1/2 times 1 x squared, which is just when x goes to 1, this is just minus 1/2. Hopefully I didn't mess the computation up, but I think it makes kind of sense. So this is what I got. Again, I think this problem was pretty straightforward. I evaluated, I saw it's a 0 over 0 case. I didn't have any exponential to bail me out, so I had to apply L'Hopital. I applied it. I got something else. I don't know what it is. I evaluated again. Got 0 over 0. I didn't get any tricks in my head to solve this without L'Hopital, so I just applied L'Hopital again. And I got this, which I could actually evaluate and get minus 2, minus 1/2. Okay, I think my reasoning was pretty standard. But any questions on this one? Okay, let's do next. This one. Consider the problem. Consider the problem. Limit when x goes to infinity of ln 1 plus x 2022 e to the minus x over x. And he has one question here. Can you apply L'Hopital to it? I think it's a good habit to form, but the best habit to form is to evaluate it first. Because if you evaluate it, you get the answer to that question, and you also get a feeling for the function. If you don't evaluate it, I don't know how you solve limits then. So again, first thing I'm going to do, I'm just going to evaluate it, see where I'm at. This is infinity. This is 1. 1 is equal to 1. I don't, I'm a genius. Now, this is infinity. This is e to the minus x. Remember what we talked about? This is 0. So what's my case? My case is infinity ln of 1 plus infinity times 0. This doesn't really look like one of my L'Hopital cases, does it? The question is, what is this? What is infinity times 0? And it is an undetermined case. Infinity times 0, again, I can make it converge to any limit you want. This is not undefined, undetermined. When you have an undetermined limit, you got to think of L'Hopital instantly. That's the only thing you have for undetermined things. You don't have anything else, maybe grouping, but there's nothing for me to group here. So I'm just going to take this part out and evaluate it separately. Limit when x goes to infinity of x2022 e to the minus x. Again, the reason I'm taking it out is because this is 0, this is infinity. I have no idea what this is equal to. This thing is undefined. So, look, I need to apply L'Hopital to this one. In order to apply L'Hopital, I need to have a fraction. So I create my fraction. Okay, e to the minus x is just 1 over ex. Oh, that's more or less clear to everyone. Now, this, we look at this for a second, and what do we see? This infinity, so you are infinity over infinity, free to apply L'Hopital. Either you do that, or you just say exponential, bigger power function. So this is just equal to, this is much bigger than this, so this is just equal to 0. Well, again, exponential much bigger than power function is something you can write on the exam. Like if you get something like that, you can write it on the exam. Now, if you have an ugly limit and you randomly see an exponential there, you know, you can't use that. But in this case, it's clear, right? I have an power or polynomial up top, exponential down below. This is clearly 0 because exponential is much bigger. Okay? And I'm done. I don't need to compute anything. So after we have evaluated this small part, I take it and I go back into my initial big limit. This is kind of similar to derivation where you just split it into smaller and smaller pieces that you can compute. And then you go back to the big one. This is the big one. And again, we had infinity here. This is 1 and this is 0. So this goes to 1. So I have log of 1, which is 0. So my case is actually 0 over infinity, which is 0. Okay? So to answer what the problem asked me, can I apply L'Hopital to this? No. That is not an undetermined case, or it's not a L'Hopital case. Okay? I could have applied L'Hopital to this thing. Yes. This I could have applied L'Hopital. But not the big one. To this thing, no. This is 0 over infinity. This is not good. Any questions on this? Yeah, so again, everything comes from the need to evaluate. If you don't have a need to evaluate, then you're never going to get solutions. It's as simple as that. At every step, you should know why you're evaluating, and have like kind of a plan to get, I mean, not necessarily to get somewhere, but knowing that you're in an indeterminate case and you need to apply L'Hopital is a plan in itself to solve the problem. Okay. So yeah, but that plan comes only after you evaluate. It's not the other way around. When you see a fraction, you're not like, I'm going to apply L'Hopital to it and it's going to work out. That's not the right way. I'm going to evaluate it, and then if I can apply L'Hopital, I'm going to apply it. Okay, now problem 11a. I've scrolled through that as well. At some point. 11a, and it asks us a lot of stuff. So let's see what we can do today. Problem 11a. I'm given this f of x that looks like this, 1 over x minus 1 e dx minus 1. And I'm asked to compute limit f of x goes to 0, limit when x goes to infinity of f of x, and limit and f prime of x. I don't know if that's a limit or it's a find or what it is, but we can get the limit of anything. So we might get the limit of this, maybe, if we're ambitious. Okay. This is my problem. Let's see where we're at. First one. Limit when x goes to 0, f of x is equal to limit when x goes to 0, 1x, 1 ex minus 1. Cool. Now let's evaluate it. X goes to 0. This is 0. This 1 over 0. This is infinity. This is 0. This is 1. 1 minus 1. 0. So everything is just infinity. So what is my case? It's infinity minus infinity. What do we know about this case? What is this equal to? Exactly, we don't know. This infinity minus infinity, undetermined case. Undetermined means we are forced to use L'Hopital in some way or another, because there's nothing to group here. In order for, so my logic is the following. Let me try to write it. So I find undetermined case. Then I know, okay, I need L'Hopital. In order for me to apply L'Hopital, I need a fraction. Okay, I can't apply L'Hopital to anything else than a fraction. I need a fraction, I create a fraction. I hope it makes sense. Okay, so now I look here. What's the easiest way for me to create a fraction? For this thing, 1 over x, 1 ex minus 1. I just bring it to the same denominator. I just bring it to the same thing underneath. So this is just equal to limit x goes to 0. This is e to the x minus 1, x e to the x minus 1. Okay? Minus x e to the x minus 1 x. Okay? Why did I do this? Because I can combine these two things right now under the same fraction. Remember, I need a fraction. That's all I'm looking for. So now my limit just became, x goes to 0, ex minus 1 minus x over x ex minus 1. Okay. Now, once I got this, I will evaluate again. I don't know, maybe something changed. It's good to be, better safe than sorry. So this is 0. This is 0, so this whole thing is 0. And here I have 1 minus 1, 0 minus 0. So I have a 0 over 0 L'Hopital case. What can I do to it? I can apply L'Hopital. That was my plan initially, right? That was my plan, so now I can put it in practice. I have limit x goes to 0, e to the x minus 1 over, what's the derivative of this? I use the product rule, ex minus 1 plus x times ex. Right. I hope derivatives are not an issue for anyone at this point. So I get to this point. What do I do now? Well, I either get a solution or I apply L'Hopital again. There's not much in between, really. So let's see what we have. This, 0. This, 1, 1 minus 1, I get 0. Underneath here, I have 1 minus 1, 0, plus 0 times 1, that's 0 again. 0 over 0, again, free to apply L'Hopital again. Some of you might ask, where do I stop? Well, the formal answer would be you stop when you get an answer. The more complicated answer would be when you realize that it's actually getting more complicated than simpler. And in this case, the idea is that it's not getting more complicated because I'm getting rid of the exponent. Slowly but surely, I'm getting rid of the exponent. Because after the next L'Hopital, I get e to the x up top. And underneath, I get e to the x plus 1 times e to the x plus x e to the x. And why did I say that I'm getting closer or that it's looking nicer? Because when I evaluate the top right now, what is that? When x goes to 0, this is 1. The idea is that if I get to make one of my parts, like either the upper part or the lower part, being equal to something that's not 0 or not infinity, I am surely done there, okay? Because I can evaluate that integral. It doesn't matter if I get infinity down below, if I get 0 down below. I know 1 over 0, and I know 1 over infinity. That is my plan. So right now, my case is 1, and whatever is underneath, I can evaluate this integral. This limit, sorry about that. Too many integrals, I guess. So I get 1 here, 1 here. This is 0 times 1, this is 0, so I get 1 over 2. Again, I think that once you get the fraction, the problem is not actually hard. I think a lot of the people will struggle to get from this original form that I have here, to the fraction form, which is here. And I can understand why this might be somewhat difficult, but I think it should make sense if you follow this simple logic. I reach an undetermined case. I need to apply L'Hopital. I can only apply L'Hopital to a fraction. I need to create a fraction. So I create a fraction in the simplest way I could find. I did it this way. There are other ways to create it. Sure, I agree with it. Maybe, yeah, I don't know. If you have your own proof, I'm more than excited to look at it. But this is what I came up with. Okay, so now once you get the fraction, I just noticed it's 0 over 0, so I can apply L'Hopital to it. Apply it. Apply it. You get something here. It's still 0 over 0, so I apply it again. And then once I got the 1 up top, I know that I have finished my problem. It doesn't even matter what's underneath, because again, let's say I would have gotten 1 over 0. I know 1 over 0 goes to infinity. I know 1 over infinity goes to 0. So it doesn't matter once I get what I get underneath, or if I can make either the top part or the bottom part through L'Hopital be a number or something, then I'm done. Okay, or get to some determined case, like I don't know, 0 over infinity, something like that. The idea is it's something there are problems, of course, where if you apply L'Hopital wrong, you can apply it for ages and you're not going to get anything. And that's why I said that sometimes you got to realize when it's getting more uglier than helpful. Okay. Is there a general rule for that? Not really. Just look at it. If it looks even worse than when you started, maybe there's something wrong there. Okay, now we're asked to get limit. We're asked to do the easier version, which is limit when x goes to infinity of 1 over x minus 1 ex minus 1. First step, again, we evaluate it. One question that I could have gotten is, can I evaluate this? Sure, you can attempt to evaluate that. We can even try evaluating that, but this one is going to be so much easier. Let me show you why. If x goes to infinity, then 1 over infinity is 0. If x goes to infinity, this goes to infinity, so this is 0 as well. So we have 0 minus 0, which is just 0. So in this case, the evaluation was really, really simple. Any questions on this? It's just, I just plugged in values. I see what I got. It worked out. Sometimes the limits are just simple. Sometimes they're not. Now, why am I saying that it's always so important to first evaluate and then do all the stupid stuff that you're planning to do? Because if you try to evaluate this one, if you try to evaluate the fraction, e to the x minus 1 minus x e to the x, what are you going to get? You're going to get infinity, 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 infinity. So you're going to get infinity minus infinity over infinity times infinity. Okay? And yes, you can solve this with some sort of exponential thing, but it's going to require more work, more places where you can make mistakes, etc., etc. So if you want to prove from this, go for it. It's your choice. I'm just going to do it like this, because I'm lazy. I'm just going to evaluate from the start and see that I have the 0 over 0. Okay, now let's see. Let's compute the derivative and be done with this problem. And then after I evaluate the derivative in my head, we'll see if we can actually compute it or not. There are some limits which are undetermined, like you can't actually solve them. But I highly doubt you're going to get one of those in this class. So don't stress about it. Well, what is f? So f of x is equal to 1 over x minus 1 ex minus 1. Okay. What is f prime of x? Well, the derivative of this is minus 1x squared. And the derivative of that is minus e to the x minus 1 squared. Okay. This looks worse than I thought. Okay, so f of x is equal to e of x minus 1, everything squared, minus 1 x squared. Okay. It's not in the problem, but we can for sure evaluate this. Limit when x goes to infinity of ex minus 1 squared minus 1 x squared. We're going to evaluate this for sure. Why? Well, we're kind of going to use the exact same logic we did before, which is x goes to infinity, x squared obviously goes to infinity, so this goes to 0. That's good. But what does this thing go to? Because in this case, I'm going to have infinity over infinity. So again, what do we do in this case? We take this thing out and we evaluate it separately. Limit x goes to infinity of ex over E2x, I think it is. E2x minus 2EX plus 1. Okay, you look at it, and here is a point, like the reason I didn't expect this to be honest, but now it makes sense. The reason that sometimes it's good to evaluate and then spend a little more time just evaluating it is because if you apply L'Hopital to this, let's just say we're going to apply L'Hopital to this. Can we? Yeah, we can, because this goes to infinity. This is infinity. Well, technically, you need a little bit more to convince me that this, because you have infinity minus infinity. So you have infinity over infinity minus infinity. So you can't even do this, to be honest. You can't even apply L'Hopital to this one. And so the trick here is, and I think I mentioned it in class, is when you have a lot of exponents, you want to get rid of them. A lot of them are not good. One exponent is best because you're going to have that exponent dominates everything else. If you have a lot of exponents, you don't know which one is bigger. Okay? So the strategy here, as I said in class, is just to divide the whole fraction by EX. So let's see. If I divide my whole fraction by EX, I'm going to get the limit. X goes to infinity. EX times E minus X, or is this writing, or EX over EX? Which one you ever want to use? I don't care. It doesn't matter. I'm going to use minus X because it just looks cleaner. 2X E minus X minus 2X E minus X plus 1 times E minus X. Right? I just multiplied the entire fraction with the E minus X. It's the same limit, of course, right? So, what is this equal to? Let's see. After we eliminate all the minus X's and whatnot. That is my limit. Let's see what I can simplify here. This goes away, this goes away, this goes away. And here, I just have e to the x left. So my limit is x to infinity, 1 e to the x minus 2 plus 1 over e minus x. So now that we've done this trick, let's evaluate again and see what happens. This is 1. This is infinity. Infinity minus 2, still infinity. Sorry, this is 1 over x. This is 1 over this infinity, so this is just 0. So I have 1 over infinity, this is equal to 0. Okay? So this trick of dividing by the exponential or getting rid of the exponential is, as you can see, extremely helpful. Now, maybe a lot of you could have just looked at this function and have an argument around the way of, hey, I have exponential to the x here, and I have e to the 2x here. So this is obviously going to be the stronger thing. So that's why I'm going to have something, this is the bottom part is going to be much, much bigger. And that is partially right. But then again, we have infinity minus infinity. So it needs a little bit of being careful here. And I'm just trying to form good habits on your side. So dividing by e of x to have this clear, undoubted function here that goes to 0 is the much, much better way. Like here on an exam, if you argue that, hey, this is e2x, it's much, much bigger than anything else, and et cetera, maybe I would definitely give some partial credit, but I would not give a formal credit unless you explain it really, really carefully. Because again, for me, you have infinity over infinity minus infinity. That is completely undefined. So I need really, really strong arguments. You either group something here with e to the x. I don't know. I just like this dividing by e to the x here because I just get something really clear and undoubted, if it makes sense. Okay, so now we turn back to our initial computation, which was limit x goes to infinity of this ex minus 1 squared minus 1 x squared. And I proved that this is 0. I know this is 0, so this is just 0. Okay. No, let's see, can we even do the next one? Maybe. Let's see. I actually don't know, but let's see. Can we even solve limit when x goes to 0 of ex minus 1 squared minus 1 x squared? Can we even solve this? Yeah, I think so. Yeah. Okay, so again, we're just gonna start by about, I think we finished all the problems on the seminar, so there's, did we? Yeah, we did. Fine. So let's see if we can evaluate this one. Again, start with the simplest case, then hopefully you just get something like something obvious and you're done. I have x0, so this is 1, this is 0, so this is 1 over 0, and this is 0, 1 over 0, so I have infinity minus infinity. As I said, this case is undetermined, so we follow the same exact logic we followed previously, which is undetermined case, I need L'Hopital, I need a fraction, I create a fraction. It's pretty simple. You know, I think there's that saying in English which goes like, necessity is the biggest teacher. You know, you'll need to apply L'Hopital, so he's gonna give you a solution how to do it. My solution is we just need to create a fraction. So let's just do that. I have limit when x goes to 0 of ex x squared over ex minus 1 x squared minus ex minus 1 squared over x squared ex minus 1. All right, and this was absolutely hideous. Let's see. We might just scrap this if it's too ugly computation. Although it's good practice, but I don't want you guys to hate me. Okay, so I created my fraction. Okay, so where are we at after all this is said and done? Maybe there's a square here. Where are we after all this is said and done? Evaluate again. I don't know. Let's see. X is 0. This is 1. This is 0. 0. And up top, I'm going to have 1, 0, 1, minus 1. So this is 0 again. Okay. This is not how I expected to go, but we just got to do it. So I have a 0 over 0 case. Like, no joke. I'm not really planning on scaring you guys or anything, but I wouldn't see any problem with something like this limit coming up on the exam. Because you have all the tools necessary to solve it. It's just computation, right? So, not my intention to scare you, but it just might happen. So, I apply L'Hopital to it, and I get limit x goes to 0 of ex x squared plus ex to x minus 2 ex minus 1 times ex. Okay, that's fine. That is fine, I guess. And here I have 2 ex minus 1 times ex x squared plus plus what? Plus ex minus 1 squared 2x. This is my computation of derivative of L'Hopital. I know it's a little bit fast, but we're kind of running out of time. So let's see and evaluate this again. Are we going to get anything better than we already have? Not really. We still get 0 over 0. So we evaluate again. We get 1, 0, 1, 0, 1, 0, 1. Doesn't look like it's going away, to be honest, which is not okay. And here I have 0, 1, 0, 0, 0, 0. Okay, so I think I would say, remember when I said that that something like this might come up on the exam? I think something like this is not going to come up on the exam. Because in my head, when I did this computation, I missed this one. If that one wasn't there, I could evaluate after the next l'hôpital. But in this case, with that one, I can't evaluate it after the next l'hôpital. So I'm assuming that you need to do like a couple of l'hôpitals and then group everything after the E of X, which I would say it's a little bit more complicated than I think that this should be. This should be for this class. Again, I'm not making the problems, but I'm thinking this might be a little bit too hard for the class. So yeah, we're just gonna leave it at that. Now I understand why maybe the problem didn't ask you to do this limit. I just thought it's a good exercise, but in my head I missed the computation. So yeah. Now, in order for me to rephrase, something like this might come up on the exam. Yes, something like this, okay? The simpler version might come up on the exam. This one is not something I would expect to come on the exam, at least not in this form, maybe without the 1 here or something. But yeah, unless you have any questions, that was all for today. And yeah, this was my last plenary session. I think Solana is taking over next week. So yeah, I'll see you in the workshop.